Thank you very much for the kind introduction. And also thanks a lot to Jan and Natalia for inviting me. It's a pity that I cannot be there today in Anchorage. I'm sure it's an unbelievable place, and you're going to have a really nice symposium. But at least I'm happy to be here online with all of you. So I will be talking about the work we are performing in 2D magnetism in van der Waals materials using first principles and always thinking by a chemical approach. So I'll start with the first slide, just introducing my lab, the 2D Smart Materials Lab at the Institute of Molecular Science in the University of Valencia. And all the work I'm going to present is performed by this very nice group of very motivated and talented people. Dorje, that just finished his PhD 1 month ago. Then also Sergio, Gonzalo, Diego, Alberto, Sourav, and Nasima. And here are our collaborators, both from the experimental side and theoretical. So most of the work I'm going to present, it has a very important contributions from other labs. So I have to acknowledge before starting all of them. And of course, the funding, we have funding from Europe, Spain, and the Valencian region, and also some collaborative projects around Europe especially. So where we are located in Valencia, that is in the east coast of Spain. The Institute of Molecular Science is placed here, just by 15-20 minutes from the city center by public transport. And it's a place where we have several groups working with crystalline organic materials, 2D materials, metal organic frameworks, both from the experimental and theoretical side. And here are some pictures about the city. It's a really nice city in Spain with very good weather and also a lot of nature around. It's a very nice place. So our group is mainly focused on code and model development using models of quantum chemistry, but also combining it with solid state physics. And we have always the idea of applying all our theory and computations are to real materials. So we are working in material science, sometimes in collaboration with experimental groups, sometimes predictions that can help experimentalists. I have been personally working, and part of my group is still working in molecular magnetism. Here are just some of our latest works. If you are interested, I'm not going to talk about that in this presentation, but here you have the references if you want to check a little bit what we have been doing in this field, because it's also of interest for you. So we have been working with metal organic frameworks, predicting how is the spin phonon coupling in these materials. Also, if you are working with lanthanide, single ion magnets, this work in collaboration with Alejandro Gaitariño was performing, correlating the data of 1,400 compounds with the chemical properties and physical properties, combining structures and to predict the physical properties. And you have also a database here, is the same data, is very interesting. Was also regarding this molecule, polyoxometallate, that has an all-muon ion here, and it behaves as a molecular spin qubit. We published this work in collaboration with the group of Eugenio and also Ars and Gardaban regarding the application of electric field to control the states of the molecular spin qubits, and also in collaboration with Janis Mausfeld. We were studying how then the vibrations are coupling this material when you are applying, for example, you apply an external magnetic field, and we can check how is this evolution, so detecting the energy levels in this system. Also, we have been working in developing models of spin phonon couplings for molecular nanomagnets, and we are also very focused, and this is the topic because it's now the main research lines in the group, with 2D materials. So I will be introducing you to the magnetism, how to tune it, how to apply also chemistry there, combining molecular van der Waals structures that are hybrid, you have molecules and the 2D material, and other related properties. Okay, just because it's a tutorial, I want to emphasize that materials are really, really important for the history of mankind. We have periods in the history that are called by a single material, like the Stone Age, Bronze Age, Iron Age, but also they influence a lot, like for example, in the Machine Age, the discovery of aluminum and how this changed the society. So always materials are really important for the development of societies. Now, we are in the plastic age and more importantly in the silicon age. So we are now in this phase, silicon or information age, that is a period of human history that started by a shift from traditional industry to an economy based on information and computerization. And this period has been characterized by fast advances in underlying component technologies, leading to continuous improvements. Computing power, but also keeping an ever decreasing cost. So now we are advancing towards the nanotechnology age. We have here this observation by Gordon Moore in 1965 that the number of transistors per inch square is doubling every 2 years. And now we are reaching a point where the size of these transistors have to be, we're in the border to the laws of quantum physics. So we have to find alternatives, new materials to keep this trend in the next years. So now we are going to this age, nanomaterials, systems with 0 dimensions like clusters, nanoparticles, quantum dots, 1D systems like carbon nanotubes, nanowires, nanorods, but also 2D materials. They can be like semiconductors, superconductors, magnets, atomically thin crystals, and the possibility of combining them. One emerging technology that we are now particularly focused is magnonics. So you know that nowadays, most of the applications that we are using are based on electronics. Electronics refers to the transport of the charge, the electric charge, well, an electric current. But when the electron is moving, it's experiencing a scattering that leads to electrical resistance, heating, and energy dissipation. And this is going to be an important bottleneck also in this process of miniaturization. So the Joule heating there is going to affect drastically the performance of the device. But as we all know here in the audience, the electrons have another fundamental property, that is the spin, that can be used to store, process, and transfer information in the form of spin waves. So in this case, a magnetic collective excitation that are transferring the information through the material using magnetic materials that can be insulators or semiconductors. And in this case, it's possible to have ultra low cost nano devices because they don't have Joule heating, and everything is based on waves. So they have also wave logics that can be helpful for quantum technologies. So these systems are also proposed to develop quantum technologies. And very importantly, this is a very, very hot topic nowadays. So here is the first roadmap that was published in 2021, when the leading experts in the field, they started to think about the next directions, that starting as a new field coming from spintronics, it was magnon spintronics, and then recognizing that this is already a new field, and detecting what are the main challenges here. So in the field, one of the challenges is to excite nano-wavelength magnons, to manipulate them on the nanoscale, because we are going through this process of miniaturization, to create nano devices with low Gilbert damping, and also to interconnect it with standard electronics. Even more recently, now this year has been accepted the 2024 Magnonics roadmap. This is the second roadmap. And here we can see that everything is going to this miniaturization of the magnetic circuit. So we are going towards this direction. And here is where the 2D magnetic materials that have been isolated in the last few years, they can be relevant because they are already at the limit of miniaturization. They can be tuned by van der Waals stacking, so making van der Waals heterostructures, and are integrable with silicon technology. So they have these properties, and that is why it's worth to do research concerning these materials. But magnetism in the 2D materials, in the realm of 2D materials, appear just recently, because we can see here the history of 2D materials. They were isolated in the labs of the University of Manchester in 2004 by Gaim and Novosello. And all the research in graphene led to the Nobel Prize to them in 2010, the same year where molybdenum disulfide was also isolated. So now semiconducting materials in 2 dimensions, the possibility of having transition from direct to indirect gap when you go to the monolayer. 1 year later, it was created the first transistor using a 2D material, in this case with molybdenum disulfide. More research regarding molybdenum disulfide, taking into account the different values of polarization. Then the dream of Richard Feynman to combine different materials to create van der Waals heterostructure was possible in 2013, but there's no magnetism at all at this point, with atoms to magnetize graphene. Other elements of the periodic table entered into the game to make single layers, for example, phosphorus, like phosphorine. And finally, in 2016, it was possible to isolate one single layer retaining long-range antiferromagnetic behavior, in this case for the iron PS3. And in 2017, the first 2D ferromagnet that is antiferromagnetic, but you have several layers, but the monolayer is a ferromagnet that was chromium iodide 3, isolated in the labs of MIT. And in the same lab, Pablo Jarillo was also possible to have the twisted bilayer graphene that is open a new field, twistronic, but it's also possible now to combine twistronic with magnetism in 2 dimensions. So are very, very recent topics, emerging areas in 2D materials. Here are the materials that we are investigating. We have been studying with the transition metal phosphorus chalcogenides that they have a nail temperature between 70 and 150 K. They are stable. It's really good because also you have different possibilities of having antiferromagnetic ordering depending on the transition metal. The family of the chromium 3 halides, that's everything started with chromium iodide 3. In this case, a Curie temperature in the monolayer of 45 Kelvin. And more recently, it was isolated a single layer of chromium sulfur bromide that is air stable and also semiconductor, in this case with the spin pointing in plane, with a Curie temperature of about around 150 K. So we are investigating these materials. I will go showing some examples of the work that we have been performing with them. And before that, I want to show you our framework. Like this is our computational and theoretical framework. We always start from first principles. This is based on density functional theory using Hubbard corrections, because we are dealing with strongly correlated orbitals, with the orbitals that are having the magnetic, are responsible for these magnetic properties. So we always start with the crystal structure, and we perform an ab initio calculation where we can get the charge density, the electronic structure, magnetic properties like magnetic moments in the system, the spin density, and so on. Then we use a process that is called linearization, that is now to derive from the ab initio calculations, from the block functions, a tie-binding model. And in this case, we use the code Vanier 90 that allows us to select projectors that are the orbitals that are playing the main role around the Fermi energy, and they are responsible for the properties that we want to take into account. And this gives us a lot of chemical intuition, because now we have orbitals that are tightly bonded, and we can understand which are the hoppings in this, between these orbitals, and how the electronic structure relates with the chemical properties. And then we calculate magnetic properties, because we are always interested in magnetism, having a spin Hamiltonian in the program TB2J that goes from tie-binding model to magnetic exchange interactions. Then we are working, and we have been developing codes to calculate the magnon dispersion. This is now in reciprocal space. And we have also simulations of spin dynamics with real-time, real space calculations. Then it's like we are creating a spin wave and see how it evolves in the material with time along space. I will start this presentation work with the works that we have been doing related chromium sulfur bromide. The first thing that this system here is the crystal structure. The system crystallizes in an orthorhombic bond group, where we have here the chromium ions that are the magnetic ions. And one thing we can see in this structure is anisotropy, because here we have along the A direction, the connection between these two chromiums is by sulfur and bromide here. And this is making almost 90 degrees, this angle here in the bonds, that this is favoring ferromagnetic interactions along this direction. If we pay attention along the B direction, we can see that now they have only a sulfur bridge here. This is around 160 degrees in the other direction, and we can see this clear anisotropy between these two magnetic ions and this chromium and chromium, but different directions, different chemical bonds. And if we take into account here just the crystal field of this distorted octahedra, here we are, this is now the B-axis, that here is pointed along Z in this representation. We can observe that we have the EG orbitals that are empty, and these T2G orbitals where we have a total spin of 3/2. So we have one of each in each of them. And by this distortion, because it's not a perfect octahedron, we have these orbitals that are stabilized in this case, this T2G orbital. Then when we do the ab initio calculation, here is a calculation using DFT plus U, we can observe both features. One thing is the dispersion that is different. If we go from gamma to X here, there's almost no dispersion in the conduction value. But when we go from gamma to Y, there's this dispersion, and this is parallel in real space to the A axis. So we are going through this direction, and we don't have this dispersion here. But when we are moving in this direction, we have highly dispersive paths here. So the system behaves as a 1D electronic system, depending on the direction. Another thing regarding this picture, this chemical picture here, we can observe that the T2G spin up component is populated here in red. We have here the EG spin up that are empty, because here is the Fermi energy, and all the 3D orbitals with the spin down component that are empty here. And we have also contributions from the p orbitals of bromide and p orbitals of sulfur. Then we go to this simplified model, deriving a tie binding model, and now we select these projectors. We select the d orbitals from chromium, the p orbitals from sulfur, p orbitals from bromide, and we fit the electronic bundle structure. So this is a calculation including Hubbard-U and spin orbit coupling, and this is our tie binding model that is reproducing very well the electronic structure. So now we have these projectors. Very, very simplified model, but is reproducing the ab initio structure because it's derived from there. Then regarding the magnetic exchange interactions, we can observe that this material, here we have, these are the first neighbors that correspond to these two here along the A-axis. And we observe that the J1 is perfectly contained along the A-axis, whereas J3 is along the B-axis in this direction, where the sulfur bridge is negating. And we have J2 between chromiums that are in different planes. So this, now we have these interactions are the main interactions in the material, and we want to calculate them. For that, we need to perform three ab initio calculations, and we have to derive 3 Barnier Hamiltonians, including a spin orbit coupling, with all the spins pointing along X, along Y, and along Z. And with this information, 3 Barnier Hamiltonians, the code directly applies Green function methods with local rigid spin of a perturbation, and we can calculate the J1, J2, and J3. In this case, we are taking a Hubbard-U of 3, because here we're varying the Hubbard-U, because the values are closer to the fit performing inelastic neutron scattering for the Magnum dispersion of this material. So this is a starting point, but of course we are always going to vary the Hubbard-U to test how this is having an influence in the magnetic properties of the system. Then, regarding the structure of this material, when we were working in this work in collaboration with Eugenio Coronado group, we were aware of this work that in that moment was in archive, where it was determined the evolution of the crystal structure with temperature. And we can observe here that when we are decreasing the temperature, the chromium sulfur bromide, the A-axis is being expanded until when it reaches around 40 Kelvin, that it remains constant, and the B and C axis are being compressed. This is a nice story because the material is behaving depending on the direction. When we are decreasing the temperature, the lattice parameters are evolving differently. And we perform here a calculation for these lattice parameters. It's calculation by Alberto. And we could observe that following the lattice parameters from the experiment and relaxing just the atomic coordinates, we observe that all J1, J3, 2, and J3 are increasing, especially J3, that is that one mediated by the sulfur bonds that are more flexible along this direction. So we can see here that there's an entanglement between the magnetism in the material and the lattice parameters. When we are going to lower temperature, the spins are more ordered and then are affecting to the structure, and the structure is following this magnetism. Here are some experimental work. Probably Eugenio is presented in his presentation there. So Eugenio was the experiments by Carla and Samuel. They were having a study of the magnetotransport properties using creating vertical heterostructures in the 2D limit, just taking 1 layer, 2 layers of chromium sulfur bromide and adding graphene. And what they found here is that it was very easy to change the orientation of the spin along the A-axis and along even the C-axis. So here they needed to change 1 Tesla to make the spins pointing along the A-axis, and with 2 Teslas having all of them in the direction of the C-axis. So it was possible to change this just with, and they were checking it with magnetotransport properties. And we were doing the calculation to see if we can make a prediction of how easy will be in a perfect material. Of course, we are having a perfect 2D material. We are not considering all the bias, but we observed adding dipolar interactions, not only the effect of the spin-orbit coupling, that with fields that are around 0.3, we could have the spins along A from B to A in the same plane. And in the case of a magnetic field of 0.8, we could put them in out of plane. So this was supporting that in this material is possible to modify the orientation of the spin with very moderate magnetic fields. Then now we have all these effects of the structure by temperature, and in this work that was published in Nanoletters in 2022, we wanted now to perform a computational experiment because we know that these materials have an outstanding deformation capacity, so we can do now a strain engineering to control the propagation of magnons in this material, taking advantage of what we observed before, that expanding the axis increases the exchange interactions, compressing P also increases. So now we want to test in point-by-point calculations how this is affecting to the properties of the material. So we started, in this case, Dorje was performing calculations of taking a single chromium sulfur bromide monolayer and doing uniaxial strain along the A direction, along the B direction. And in this case, keeping, for example, Haber-U constant, we can observe the trend of 1 magnetic string interaction. So we were also varying the Haber-U in all the calculations and the different factors of strain and fitting using the least square method to have these high density maps of how a exchange interaction is evolving with U and with strain. We can observe here that we are with Haber, in this case, like when we are keeping, for example, for a particular Haber-U, we are now performing a strain, and when we expand the material along this direction, the J1 is increasing. And this is directed because we are applying along the A direction, and J1, as I said before, is contained in this direction. Then one advantage of working with these Barnier functions and TV2J is that it allows us to have an orbital decomposition of the magnetic string interaction channels. So we can observe which are the mechanisms that are competing to give these values of the magnetic string interaction. And in this case, we have a competition between this mechanism that goes from orbitals that are dxy in one chromium to the dz squared in the other one. And this is a ferromagnetic interaction because it goes from one T2J orbitals to each. The spin is a ferromagnetic because it's keeping the same orientation. It can go there, it's empty. Whereas we have this antiferromagnetic interaction between the dxy orbitals, T2G, T2G, because in this case we have already filled with this 1, 1, and 1, with 3 spin up in each one of the T2G orbitals, and the hopping only can go antiferromagnetic. When we are expanding the material along these directions, we are decreasing this antiferromagnetic interaction. And this is the main effect, because we can observe here that the other mechanism, the T2GG, is almost constant. So the enhancement of J1 comes from this mechanism that we're fighting when we are pushing these two atoms, these two chromium atoms apart. Regarding the other strain that we apply in the calculations along B, in this case, this is in the direction of J3. So we can observe here that J3 is increasing when we are, this is negative, so this is compressing the material. So we have now the opposite trend. And in this case, there are these two mechanisms. This is the ferromagnetic one, coming from a T2G orbital to a G, from the dxz to the dz squared. And this is increasing when we are compressing the material. And on the other hand, this EG path that is also being decreased here. So we have at the end, this is making that the compression is enhancing the value of J3. And then we can calculate the Magnum dispersion with this exchange interaction we have calculated performing the Holstein-Primakov transformation. And in this case, we are now seeing how it's evolving, the Magnum dispersion, when we are expanding the material. So as I said before, uniaxial strain along A is increasing, the exchange interaction. And we can see here the final picture. So when we are increasing, we are affecting mostly this gamma X direction in reciprocal space that is parallel to the A-axis in real space. And we are increasing here the dispersion. So this is making that these waves are traveling faster. And we are also affecting here the Magnum gap, that is coming more as an effect in the anisotropy, but we can observe here that this is also increasing. This is the blue line expanding at 5% our material. When we are applying a long strain along B, in this case, along the B axis, we have the opposite. Now we are expanding the material and this is decreasing, and we are affecting most this gamma Y direction, and the dispersion is being decreased when we are expanding the material. So we have the opposite behavior. In this case, the compression is what is making these waves to travel faster along this direction. And this can be observed also the opposite trend. The colors now are inverted for the Magnum gap here around gamma. Then we calculated the Curie temperature of the material using from the Magnum dispersion relation, but we are using renormalized spin wave theory with this self-consistent expression. So that was reported by Joselado in this work. And in this case, we can observe that we achieve a value of 122, experimental is 146, so it's pretty close for this kind of prediction. And we can observe that when we are increasing along A, we have expansion, like the material is expanding and the Curie temperature is being enhanced. We calculated also the evolution of the Magnum gap, this that I mentioned around the gamma, and we can observe this nice trend. No? For example, in this case, we can observe that the Magnum gap is being increased when we are increasing the Hubbard U in the calculations for this kind of strain. But this is not translated into an enhancement in the Curie temperature, because in this area, we are favoring antiferromagnetic interaction. So when we are favoring antiferromagnetic, it's competing with this anisotropy in the material, and we are not increasing the Curie temperature. We need to be in this region here. This is more like just performing expansion of the material, the temperature will increase. And for the inertial strain along B, we have this opposite. In this case, we have to fight these EG-EG interactions that are making J3 antiferromagnetic. Even if we go to extreme cases in the calculation, this will be an antiferromagnet, the material. The material will have antiferromagnetic interactions stabilized in this case. Then once we have this, we can also go to real space and real time, and we can study how is this spin wave propagation. For that, we use the Landau-Lipschitz-Gilbert equation that is making the precession of the spins, and we have a term of damping that is making that at the end the spin wave ends, so it's relaxing. And for that, we use Gilbert damping from literature. In this case, we use the one of chromium iodine 3. So this is a phenomenological approach, but taken from a related material. Now we are working in implementing ab initio calculations to determine this for each material. And to create a spin wave, we provide an ultra short oscillating magnetic field during 1 picosecond to generate a wave. So here we can see the effects between the chromium sulfur bromide without any kind of strain and expanding along the A-axis. So we can see here the simulation, and we will observe how the waves now with this 5% strain are traveling faster along the X direction, that is along the A direction in the crystal. And then now we can check for the compressive strain. We are going in the case of along B, and we can observe now that the material, the spin waves with this compression are traveling faster along the Y direction. So this reaches a group velocity of 7.5 kilometers per second according to this calculation. So the effect is mostly like if we want to play with this compression along B will make the material, the waves traveling faster in this direction. Then another possibility that we are now exploring is the possibility of controlling the spin waves using chemistry. The idea is to use, for example, stimuli-responsive molecules to combine with 2D magnetic materials for applications in magnetics. No? It can be called molecular 2D magnetics. So the idea is to use the power and versatility of chemistry to excite, modulate, and also detect spin waves in hybrid molecular 2D heterostructures formed by these organic molecules, for example. This is the first approach that we have been performing, and 2D magnetic material. So here is a 3D animation of the concept. We have a coronine molecule that is deposited on the surface of a 2D magnetic material. We have the possibility of exciting with light, so making transition in the energy levels of the molecule. And as we have a magnetic dipole between the molecule and the 2D material, we can generate a spin wave, and then it will propagate along the material, and we can even think of placing other molecules to detect the effects of the propagation of the spin wave. But we are also tuning directly the properties in the 2D material. That's important. We have started studying these organic molecules. We have focused mainly in donors because we have chromium sulfur bromide, that we have these bromide atoms that they have high electronegativity. And we have been studying coronine, pereline, and TTF, but we also wanted to test an acceptor, in this case, the TCNQ. This is the first work towards this molecular control magnetics. To do this kind of calculation, we have to test different absorption sites in the material and also different orientation of the molecules. These are expensive calculations. We need to work with large supercells, in this case 4x4 supercells, to ensure a distance of around 12 angstroms between the molecules, and we have to add also dispersion corrections. And with this, we calculate the absorption energy from the different positions of the molecule on top of a chromium ion, on top of sulfur, top of bromide, hollow. So we have to test all these possibilities. These are, after the calculation, the most stable sites for each one of the molecules. So in the case of pereline, is top of a bromide. The case of coronine, top of chromium. TTF is in this area that we call a hollow between this bromide and chromium and the sulfur. And in the case of TCMQ, is on top of a bromide. But we also were testing all the different possibilities of orientation of the molecule. And this work was published very recently in Nanoscale Advances, and you can check there all the calculations that we performed. It was more than 1 year of calculations, because it takes a lot of time on this kind of systems. And we observe also that, for example, in the case of perilene and coronene and TCNQ, they are in this position that we found. They are in this perfectly aligned orientation in the top of one atom and taking directly one of these along one of the axes, in the material. But in the case of the TTF, the most stable calculation is 165 degrees. So the molecule is tilted, and it's also tilted towards a bromide that we will see in the next slide. Regarding the energies, all of them are negative, so they are possible, they are stable in this surface. We were testing TTF, perilene, coronene, and TCNQ, but as the best result we got were for TTF, that has this absorption energy of minus 0.6 electron volts. It is closer at 2.1 angstrom to the surface, and we have this 0.7 electron transfer. We wanted to increase the donor character of this molecule, because the most donor is the better in this case. And we add a methyl group here in the TTF. We substitute the hydrogens, and we observe a better absorption energy. The molecule got closer and more electron transfer. So we have a good tandem now to control the properties in the chromium sulfur bromide by molecule. This is the charge density. We observe here what I said before, that the molecule is tilted towards a bromide. Here, this means that in this case, it's a depletion of electron density that is going to the bromide here. And this is the case of the TTF, and this is the TTF with methyl, TTF-CS3, and this is the TTF. They're very similar, but in this case, it's even increasing the charge transfer. Then we have here the coronene, perilene, and the case of the acceptor, the TCNQ, that is almost just accepting a little bit, is not performing any kind of change in the properties here. Then we take the donors that are the important ones, and we can see this nice correlation. So we are adding here the charge transfer that we got from the initial calculation, that are these blue dots, and we can observe that we are going from TTF to TTS-CS3, but we also did a very fast calculation of getting the highest occupied molecular orbital, the energy of the HOMO, of the donor of the molecules separately, just point by point calculation of these molecules, and then the conduction band minimum of the acceptor. And we relate these two properties, the charge transfer from the initio with we plot it versus this energy difference, we can get this very nice correlation. So now, if we have a different molecule, we can calculate the HOMO, and as we know already, the conduction band minimum of the acceptor, we can predict more or less how much charge transfer is going to give to the material. And this is important because then it's related how this is going to affect the magnetic properties in the material. Well, in this case, we wanted also to check what happens with the structure. So when we have chromium sulfur bromide, we have this chemical bond along the B-axis by sulfur bridges of 158 degrees. And in all the cases, this is being enhanced by the presence of the molecule, except the TCNQ that is not affecting that much, but in general, all of them are affecting towards an increase of this bond. This is not good because this increase of the bond makes that the J3 decreases. This is just the effect of the structure. But other thing is the effect of the charge transfer. So if we calculate just the distortion of the chromium sulfur bromide, we can observe here in J3 how this is the 2.8 is the J3 millivs for the chromium sulfur bromide, but this is clearly decreased by the effect of this change in the sulfur bonds between the chromium along this direction. But then when we activate, because here we are removing the molecule from the calculation, just taking the distortion. When we activate in the calculation the atoms that come from the molecule, there is the charge transfer, and we increase clearly the J3, especially in the case of the TTF CS3, but also is increasing in the case of the TTF. So this is the effect by the charge transfer directly. We can compare these two calculations. Then we wanted to see what happened. Now we take this is the calculation taking into account the molecule. We have here the J1 that is in red, J2 and J3. And we can now add directly only doping to the unit cell. We remove all the supercell, we take just the unit cell of chromium sulfur bromide, and adding the doping, we get very similar results of J1, J2, J3. So if we know more or less the charge transfer, just doping the 2D material, we can get a good estimation of the exchange interactions in this system. This is one really advantage of having now this relation between the energy of the HOMO and the conduction band minimum. And here we have also the effect of the distortion that we observed, that then the effect of charge transfer is increasing this from the distortion. Regarding the magnon dispersion, we observed, especially here in the gamma Y, because we are affecting mostly J3, as I said before. So we have the TTF CS3 that is increasing the group velocity, and also the TTF. The black is the pristine, and the other ones, because of the effect of the distortion, they are decreasing the group velocity. So it's a way of tuning the magnon frequencies by using molecules, by charge transfer, especially in the main mechanism. We were also investigating now the potential of this material as a magnon sensor. Now, instead of using organic molecules, we were placing gas species, pollutants, and we were studying all these pollutants, like, for example, ammonia, NO2, CO, CO2. And in this case, we observed that the absorption energy is much smaller than in the case of the organic molecules, and also the charge transfer. But we wanted to investigate also the effect of the vacancies in this material, because these materials, we know that it has been reported in this work, for example, in ACS Nano in last year, that it has vacancies of bromide and also vacancies of sulfur. So we wanted to test what is the effect is for the absorption of the gas molecule. So we are comparing here the absorption energy on pristine chromium sulfur bromide, that is in blue, of this species. And then we add vacancies. We have a supercell. We remove one of the bromide. We relax the structure, and we add the molecules. And we can observe here that for the molecules that have nitrogen, this increases a lot for ammonia, NO, and NO2. And in the case of the vacancies of sulfur, there's some increase also here. The effect is not as drastic, and when we have these vacancies of bromide that are the most like the most that have more probability to have in this material. So it's a good material to capture this kind of gas molecules. And then we wanted also to check what happens in the magnons, like to test it with magnon transport, for example. So we have here that when we have the pristine material, there's some effect here for the NO, this increase in the group velocity here, but the effects are not very drastic. But when we are taking into account now the vacancies in the bromide in bromide atoms, we can observe clearly that the magnon dispersion is changing in the material. And we are now for these molecules that are chemisol, so it will be like having magnons transport to test that the material has captured a gas species. So there is the idea of having a kind of magnon sensor for capturing these gas species. This has been published very recently in Chemistry European Journal, as is one of the covers of the journals. Then we have been also working with chromium iodide 3. In this case, unrelated, chromium chloride 3 and chromium bromide 3. So these systems are also interesting for magnonics because we have, in the magnon dispersion, there's a Dirac cone, similar to the Dirac cone in the electronic properties, but in this case in the magnons, because they have hexagonal unit cell, and especially in the case of chromium iodide 3, this Dirac cone is open. There's an opening here, and this leads to topological magnons. So they are magnons that are more robust in this case. We were also testing now the effect of a strain to test the effect on this magnon gap in the Dirac cones in the magnon dispersion, and testing now the effect of exchange interactions and so on. And in this case, we can observe that in the case of chromium iodide 3, the exchange interactions are higher. We have the spin orbit coupling in the iodine that is mediated. We wanted to follow a fully ab initio zero free parameter methodology in this case. So we are calculating for each step in the strain, we calculate self-consistent the Hubbard-U. We are now not varying the Hubbard-U for the magnons because we wanted to do everything fully ab initio and test what is the effect of this Hubbard-U in the calculations. So we derive here is the spin Hamiltonian for this system. So we have the exchange interaction, here is the magnetic anisotropy and the exchange interaction. We can add isotropic and anisotropic magnetic exchange interaction, but also add the Alositsky-Morilla interaction. So when we cancel this interaction, we observe that we have a Dirac cone in the magnon dispersion in K for all three materials. This is normal by symmetry in this material. But then when we activate the DMI, we observe that the gap is not open for the chromium chloride 3, it's slightly open for the bromide, but we have here a clearly gap during this fully ab initio in the kappa, in the K point. Sorry. So with this, we can predict, just following a full ab initio, that this comes from the Alositsky-Morilla interaction, this opening of the gap, and then we can tune it with a strain, like forming the axial strain. We can observe here how this is evolving, how the structure is evolving, and if we apply 5% of a strain, we are increasing this gap. This is the main effect, that this is compression, this is expansion, and we can observe that with this expansion, we are tuning directly the Alositsky-Morilla interaction, and we can reach a higher value of this magnon gap. And this is the value that we obtain fully ab initio, being more or less twice the value of the real magnon gap determined by an elastic neutron scattering. Then regarding the transition metal phosphorus trichalcogenase, one thing that is really interesting in this material is that depending on the transition metal, we can have different magnetic orders. All of them are 2D antiferromagnets, but in the case of the iron, we have spins out of plane and following these zigzag chains. In the case of nickel, they are also zigzag, but the spins are in plane. And in the case of manganese, we have nil magnetism. So all the interactions are antiferromagnetic. These studies are relevant because they have been also measuring and creating magnons in this material. And they are antiferromagnets that in principle with antiferromagnets, we can go up to terahertz frequencies. Here are some of the works that we have been doing in collaboration also with the group of Maria Ramos and Reyes Calvo in Alicante. And we were determining Hubbard-U from the calculations, so from the experiments they have for the gap, the semiconducting gap, and this was around 1.9, 2.2 electron volts, and also testing the effect of charge transfer when we create van der Waals heterostructure, that in this case was increasing the luminescence of the molybdenum sulfide. So this possibility always to combine different materials, and with having initial calculations, we can predict what is happening. Also, in collaboration with the group of Mirko Cinquetti, we were simulating the ARPES. In this case, we compared the experiment with the theory. In this case, the Hubbard-U that we are matching is very similar to the one that we obtained in the previous work. So 1.9, 2.2 was in that range. And this was fitting this gap between these two electronic states here in the ARPES experiment. And here we have the calculation. So this is reproducing very well the different curves. So this is an ARPES simulation. And we were also getting, so for the different cuts of energy, the rich band structure, and we could determine which are the orbitals that are playing the main role here, that are the iron 3D orbitals. This was also published last year in Materials to the Electron. So other work in collaboration with experimentalists, in this case, also the samples from Eugenio and experiments in Delft by the group of Van der Zand. And in this case, they were working with membranes of this material, with iron PS3, cobalt PS3, and nickel PS3. And interestingly, they observed in the experiments that, for example, in the case of cobalt, that the material, when the temperature is decreasing, the magnetism, so this is the Nel temperature, we're going to low temperature, the magnetism is being compress along the A-axis and is expanded along the B-axis. And when we have nickel, the effect is not happening. So with nickel, everything is isotropic here, but we have this peanut shape in the case of the iron and the cobalt, that in this case are experiments for the cobalt, that are reproducing, so that are a mark of this effect. If we perform a fully ab initio calculation, in this case, with no external parameter, we observe that effect. We observe a compression of the A-axis and expansion of the B-axis for the cobalt. This is also happening for the iron, and nothing is happening for the nickel. This is almost very constant. We were testing also different magnetic orders, and then the effects go in different directions. So it's very related with the magnetism. Magnetism is driving all these interactions. Then we go to our orbital resolve model to test what are along these directions the main mechanisms. And we have two ferromagnetic mechanisms. One is in J1 along this direction, another one is in J2 along this direction. In this case, the material behaves ferromagnetic along this direction. So the system with this kind of compression along this direction is favoring the hopping of this electron from the dxz orbital here to this one that is empty, for this pair to this pair. And in the case of this direction, this expansion is making more difficult this hopping, because here we have antiferromagnetic interaction. And this is also open here, and the material is performing this. If we go now to nickel, in the case of nickel, all these states, the T2G, are fully occupied. It's at D8, and in this case, this is cancelled and this is cancelled, so the material cannot provide this kind of enhancement of these properties, because the mechanisms are already taking, they don't take any place. They cannot hold the electrons because everything is full here. Then another example we have been studying is the possibility of tuning with chemistry, designing a Janus 2D material. In this case, the two phases of the material are asymmetric, and we wanted to test what happens when we have sulfur here and selenium in the other phase. This was published in Dalton Transactions, and in this case, it's called a Janus because this Roman god that is looking to the future and to the past, so two different phases. And now we are breaking symmetries and we want to test this effect. So regarding the magnetic order, we are getting very similar results, the magnetic order, but we are increasing the magnetic anisotropy energy. And this is what happens in the case of the nickel, that we are changing the sign. This means that we are also making the spins out of plane in the case of the nickel when we are doping with a Janus structure, and we are enhancing these Gauss-Morilla interactions, and this is making a big effect on the magnon dispersion for the Janus. Then, okay. Yeah, I think, how much time I have?
About 2 or 3 minutes left.
Okay, I'm almost finishing. Just introducing this very recent work that we have been published. We are comparing the properties of iron gallium telluride with iron germanium telluride. They have similar chemical structure, just replacing gallium by tellurium, and there's a big enhancement of the Curie temperature. And we observe that when we have interactions that are in the same plane, in this case, in the case of germanium, this is antiferromagnetic, and we should switch to a ferromagnetic one here. And this is in the bulk, but when we go to the monolayer, we have the same effect. So are these interactions that are responsible of this enhancement of the temperature, according to our calculations? And we can also explore which are the mechanisms. This is just coming from the interactions that are ferromagnetic or antiferromagnetic. And the last thing, we have this has been published just this week, well, accepted this week. And in this case, we have tested the effect of TCNQ on iron germanium tellurium. This is a nice collaboration with Mike Shatrup that is there in the conference, so he will be able to give more details about all the experimental part. And we observe in this case that electron transfer is very important in this material. This makes the coercivity of the iron germanium tellurium to increase 5 times. And when we have this whole doping, we are increasing the exchange interactions that are interrelated. between the layers. So this is the main reason, and it's not an effect in the magnetic anisotropy energy, the key in this structure. So this is the last work that we have been working in the last months. So some take-home messages: 2D magnetic materials are a fascinating playground to explore and control the magnetic properties. When we combine ab initio calculation with a tight binding that is derived from ab initio, we can have practical guidelines with chemical intuition for the design and optimization of these materials. And we have also proved the versatility of chemistry that can open a lot of new opportunities in this emerging field of mathematics. With this, I finish my presentation. I thank you very much for your kind attention, and I'm open for discussion. Thank you very much.
So we have time for a few questions. If you want to, you can come up closer to the microphone so Jose can hear you clearly if you have a question. Anyone has a question for Jose? Okay, someone's coming up to the mic now.
Using the computer. Okay, thank you for that nice talk. So you were showing this plots where you have a molecule on the surface of 2D material and their waves come out, right? And so what you're actually picturing in the waves, the molecules which you were talking about, they're not by default magnetic, right? So kind of, yeah,
Must be plasmonics, right?
yeah. So well, so yeah, so that is probably more some in the electrical part of the electromagnetic wave, which matters, right?
Yeah, thank you very much for the question. Well, in this case, are spin waves that we have. So the material, because it's a magnetic insulator, it has the possibility of getting this excited magnetic interaction. So we have spin waves in the material. But what we are changing is the population of the orbitals. So the magnetic moments in these magnetic atoms, and we are also changing the bonds, and so it's an effect in the electronic structures, but it's affecting the distortion, but also an effect into the population of the energy levels, so the states that we have in the system. And this makes a change in the magnetic exchange interaction that is key for the propagation of these waves, because they depend a lot on how two spins are interacting to propagate these waves. So we are changing the interaction towards, so thanks to the effect of the molecule. We are, for example, adding electron density, we change the population, we change the magnetic moments, we change the magnetic exchange interaction, and this makes that the wave can travel, for example, faster along one direction.
Yeah, Jose Jaime, this is Jan. I would follow up on that and ask again. So when you place a molecule on the surface, you're basically doping the surface, right? So you're getting some kind of charge transfer to the surface that you can predict. And you're basically launching some kind of charge wave, like a plasmonic wave, right? That you launch because of that charge transfer, right?
Yeah, but the main effect.
So to go back, presumably you could do that same kind of thing, even without a molecule on the surface. You could do it with light, right? Because it's just like doping a polymer with, say, I3 minus versus with light. You get the same kind of charge transfer and charge defect states, because I'm sure that Sumit Mazumdar knows this well from the old polymer days, right?
Yeah, exactly, because with with light you can generate already the spin wave, and you could control but the advantage here of the molecule is that you can fine-tune the frequencies. You can fine-tune this effect of the like, for example, we replace a hydrogen by a metal group, and then we change the doping, and this is having an effect. So it's a way of controlling using a chemical design, no? Which is the best molecule to induce. But of course, with light, it's possible to generate the spin waves and also to modulate the spin waves.
Right, but you only get one chance. When you bring the molecule down to the surface, you get one chance to launch your wave. That's when the molecule binds to the surface. With light, can pulse many times and you can have many waves of different types, right? Because you only have one charge transfer per molecule.
Yeah, but the effect, for example, in the, like, for example, when you have the magnetic effect, no, for example, you can have a molecule that also is spin polarized. Then you have a magnetic dipole there induced, and with light, you can control the molecule to create the spin wave. No, this is like amplifying, for example, the signal of the light towards a molecule, depending on the energy levels that this molecule has. So it makes a lot of playing for also for the chemists, no? Like to think about which are the best combinations between one material. Is with light, it's possible to generate, and you can tune, but you have much more versatility because you can combine both effects. You can combine light with the molecule and then the material. It's more complex at the end, but it's a richer playground, as you say.
We have time for one final question. Well, Jose, I had a question. This is something that came up a little bit earlier. We were talking about basically how well theory can predict some of the experimental results in a previous talk. And so you had mentioned at the beginning of towards the beginning of your conversation, a paper you published that was talking about the physical parameters of that theory had predicted, like physical properties and things like that. How accurate was that? Have those results been shown experimentally afterwards? Have they been tested experimentally?
Yeah, like for example, in the case that we are for the Magnon gap, that this is a very fine
launch of
sorry. For example, in the case of the Magnon gap for the topological magnons, we are having double the effect of the calculation. So it's a factor of 2, but for a very, very teeny region, like we are talking about 1.3 milliVs versus 0.7 milliVs. In the case of the exchange interaction, it depends a lot on how we tune the Hubbard-U. That's one thing. No? For example, we are fitting the Magnon dispersion of the chromium sulfur bromide, and then for a Hubbard-U around 3, we can get a very good description. We are very close, and the Curie temperature is, we are predicting 122 instead of 146. So for this, because we are never like, our calculation is always based on an ideal model of a perfect 2D material. We don't have the substrate and all these effects. So at the end, I will say that they are pretty accurate in terms of prediction, in terms of getting a good estimation of exchange interaction. But of course, they are not perfect because we are relying on several assumptions to make this more efficient, no? Because we start from ab initio, we go with tie binding, and in all these paths, we are making some assumptions that are changing. But I will say that we can go up to very, very close results, like for exchange interaction, for example, that are key for the Magnon dispersion.
Thank you very much. It makes sense. Everyone, let's give Jose another hand clap.
Thank you very much.